Suppose you are predicting house prices from two features, the square footage, which runs into the thousands, and the number of bedrooms, which sits between 1 and 5. To many machine learning models, the square footage simply looks 1,000 times more important, purely because its numbers are bigger. That single quirk can quietly wreck your model, and the fix is a pre-processing step so simple it is easy to skip. It is called feature scaling, and getting it right matters more than you would think. Let's dig in. So what actually goes wrong when features live on wildly different scales? Here it is side by side. Feed a model raw features in mixed units, and the big numbers take over. Any method that measures distance between points or follows gradients downhill gets dominated by whichever feature spans the largest range. Square footage drowns out bedrooms, not because it matters more, but simply because its raw values are larger. Scaled features put every input on a fair, comparable range. Once each feature is risk-scaled to a similar spread, distance and gradient methods weigh them on their merits rather than their units. Now, bedrooms and square footage each get a real say. The geometry of the data becomes meaningful, and the model can actually learn which feature carries the signal. Scaling is easy to get subtly wrong, so follow the correct procedure one step at a time. Watch the order carefully. First, choose your scaler. Standardization, the z-score, recenters each feature to a mean of 0 and a standard deviation of 1, which suits data that is roughly bell-shaped. Normalization, the min-max approach, instead squeezes each feature into a fixed range like 0 to 1. Either one puts your features on comparable footing. Now, the step everyone rushes, fit the scaler on the training data only. Compute the mean, the spread, the minimum and maximum from the training set alone, and never let the validation or test rows influence those numbers. This is the discipline that keeps your evaluation honest. With those statistics locked in, apply the very same transform to your validation and test data. You are deliberately using training error numbers on unseen rows, because at prediction time, that is all you will ever have. Computing fresh statistics on the test set would leak information and quietly inflate your scores. Only now do you train the model on features that finally share a comparable range. Distance-based methods, gradient descent, and regularized regression all behave, converging faster and treating every feature fairly. Get this order right, and scaling becomes an invisible, reliable foundation under everything else. Strip it down, and 3 ideas capture everything about feature scaling. The core purpose is fairness of range. Scaling rewrites every feature onto a comparable numeric scale so that no single column dominates a model just because its units happen to be large. It changes the numbers, never the underlying information they carry. The second idea is knowing when you need it. Scaling is essential for distance-based methods like k-nearest neighbors, k-means, and support vector machines, for gradient descent where it speeds convergence, and for regularized regression where the penalty must treat every coefficient fairly. Tree-based models like random forests and XGBoost, however, split on thresholds and simply do not care. The third idea is a rule you break at your peril. Always fit the scaler on the training data alone, then reuse those statistics everywhere else. Computing the scaling over the full data set leaks information from test into train and inflates your results, so scaling always belongs inside your training pipeline. All right, let's lock in the essentials. Feature scaling puts every input feature on a comparable numeric range, so no single feature dominates a model just because its units are large. Standardization risk scales each feature to a mean of 0 and a standard deviation of 1, while normalization squeezes each feature into a fixed range like 0 to 1. It is essential for distance-based and gradient-trained models and for regularized regression, but tree-based models like random forest and XGBoost do not need it at all. The golden rule is to fit the scalar on your training data only, then apply those same statistics to validation and test, where you leak information and fool yourself. If preprocessing explained this plainly is your thing, we unpack a great deal more of it over at standarity.com. We'll see you there.